Now that I've introduced decision-making and looping structures, we can start doing some fairly sophisticated programming. Usually, this includes a lot of calculations, which can become very time-consuming. So one facet of numerical analysis is to create code that provides results in a reasonable amount of time. This video gives a few tips as to what might help or hurt the efficiency of your code. The first issue I'll cover is the use of loops versus Octave's built-in array operators. Executing looping structures is usually more time-consuming than performing a similar operation using array or matrix operators. This is because looping structures operate on individual array elements, while array operators work with multiple elements at a time. For example, consider the element-by-element multiplication of two arrays. Suppose I want to create an array C that's the product of matrices A and B. To get C, you multiply the corresponding elements in A and B. This process can be implemented as a set of nested for loops, as shown here. For any combination of n and m, C of m comma n is the product of the elements of A and B at that location. The nested loops just create every possible combination of m and n. The elements in C are created one at a time. On the other hand, Octave's built-in array operators perform a process called vectorization. That means that operations are executed using all of the elements in the arrays at once. This usually results in operations being executed faster than if they were implemented using for loops. So in general, multiplying our two matrices from the previous example can be done a lot faster by using dot times to do the multiplication rather than the for loops. There are a couple of other ways to improve efficiency, even if you're writing your own looping structures. One approach is to pre-allocate memory for arrays that you will be creating in your loops. When you change the size of an existing array, Octave has to request additional memory to accommodate the increased size. So if you're creating an array element by element, every time your loop adds to the size of an array, Octave has to take time out from computing and go ask the CPU for more memory. On the other hand, if you know that your loop will create an array with 100 rows and 100 columns, one element at a time, you can use the zeros command, for example, to create a 100 by 100 array of zeros before entering the loop. Then the loop will just overwrite existing values and no time needs to be taken out to change the amount of memory. Displaying the results of calculations to the computer screen is really time-consuming. So if you're executing looping structures that perform a lot of calculations, suppress the display of the calculation results by following that line with a semicolon. If you want to find out how long a section of code takes to execute, you can use Octave's tick and tock commands. Type tick just before the code you want to time, and tock just after that code segment, and Octave measures the amount of time between when those commands are executed, and that result is displayed to the screen. Tick and tock measure the total elapsed time, not just the time Octave spends executing code. Operations that your computer is performing in the background can affect how long it takes for the code to execute. So you may find that the results you get from using the tick and tock commands vary from time to time when you run your code. Now I'll show how these approaches look in Octave. Here are the equations I'm going to implement. These equations govern the current in an inductor that's subjected to a voltage pulse. The details aren't important for us. I'm just using this as a programming example. The current's given by this equation for time from 0 to 1 second, and by this equation for time greater than 1 second. I want to calculate the current for times 0 to 3 seconds at intervals of 1 microsecond. I'm going to end up calculating 3 million values for current. In the demo for this example, I'll use both looping structures and array operators to evaluate these equations and compare the time required for each approach. First, I set all the constants and a vector containing the times. The first approach I use to calculate the current in this file is to just loop through the time values, check whether the time is less than or greater than 1, and evaluate the appropriate current equation for the appropriate time. I've bracketed the set of code with the tick and tock commands, so Octave will display the time elapsed while executing this code. The next approach is the same as the previous one, but I use the zeros command to pre-allocate memory for the current values before entering the loop. Again, the tick and tock commands display the elapsed time. Notice that I clear the old values for current before doing this, so I can get a time estimate that's consistent with the first approach. Next, I'll use array operations. First, I pre-allocate memory for I. Then I use the find command to determine which equation to apply to the values. So the values of current corresponding to times less than or equal to 1 are calculated here. The values of current corresponding to times greater than 1 are calculated here. As usual, the tick and tock commands are used to find out how long this process takes. Now I'll run the code. Using a for loop with no pre-allocation of memory, the code took over a minute to run. Pre-allocating memory reduced that number significantly, but eliminating loops entirely and using the find command used almost no time. These numbers will vary depending on the computer and what programs you might have running in the background. That ends my introduction to Octave programming. Next, I'll finally start talking specifically about numerical analysis and solving engineering types of problems using Octave. However, the programming tools I've introduced so far will be used throughout the rest of the course, so you get plenty of practice with creating functions and decision-making and looping structures.